Hello YouTube, welcome back. Today we'll do a very quick summary of what we did today. What is a polynomial? We were given, this is section 3, chapter 3. We were given, let's see, what were we given? This is question 17 from the homework page 205. I think you had multiples of 10, no, multiples of 5 tonight. Okay, so you're given, what were you given? Oh, you were given 3 roots. You were given a root at x equals 7, and a root at x equals -3, and the multiplicity at -3 was 2. So we're evaluating, or we're analyzing this function 3 times x minus 7 times x plus 3 squared. And so we wanted to find the mins and the maxes and what happens at the roots and that kind of stuff. Okay, so this, and by the way, if you FOIL this out, of course, it's going to be a cubic. So the first thing we're going to do, is we're going to define that function, and we're going to show it. Okay, so I guess I skipped a step. We were given that x equals 7 and x equals -3 were roots. All right, so there's the function. All right, and if now the question is, what does it look like if we FOIL it out? Obviously, it's a cubic. So the end behavior would be like an x cubed function, or 3x cubed. Power function. The limit at infinity is positive infinity, the limit at negative infinity is negative infinity, but then local behavior near the roots or near the x-intercepts and stuff like that is a little bit different than just power function, right? So let's expand. In other words, FOIL it out. And you get 3x cubed minus 3x squared minus 99x minus 189. And is that the depressed cubic, by the way? No, it's not. It's got 4 terms. Okay, good. That's fine. All right, so then the next thing is find the limit at infinity. So we could say, this is how we do this in Sage. We can say find the limit of f of x as x approaches negative infinity. Now, if it's like a power function, an odd power function, it should go to negative infinity. Let's find out. There you go. Okay, and what's the limit at positive infinity? Here's the syntax of that. The limit is of f of x as x approaches positive infinity. And if it's just like an odd power function, it should go to positive infinity, and it does. There you go. Perfect. Very nice. All right. Then let's see what this thing looks like. Let's graph it. Now notice what happens when you have an even multiplicity at x equals -3. So we know the x-intercepts, right? We know at x equals 7, there's a root, an x-intercept, and an x equals -3. But look how it's different at -3 and at positive 7. Let's take a look at the graph. So we're plotting f of x from -4 to 8, so it includes those roots. All right, so we have an x-intercept. Oops, make it a little bigger. At x equals -3 and an x-intercept at x equals positive 7. But notice the intercept at 7 has an odd multiplicity, so the graph goes through the x-axis at that x-intercept, but it bounces off x equals -3. All right, so the x-intercepts are at -3, 0 and at 7, 0. And we could also get the y-intercepts, I suppose. I don't think I put that in there. Just for fun, why don't we do that? Let's do... how about this? Okay, let's show f of 0. All right, so if we plug in x for 0, we get the y-intercept. Just like as if we plug in y equals 0 when we solve for x, we get the x-intercepts. And so where is it that it's hitting the x-axis? Well, let's see. If you plug in 0 here, you should get -189, right? Let's see. Yep, -189. There it goes. Okay, the next thing is, okay, can we find local mins and maxes? That's what was new this time. So we know the domain, all real numbers. We know the range, all real numbers. We know the limits at infinity. We know the x and y intercepts, but we don't really know this thing about relative min and relative max, or local min and local max. What does that mean? Well, take a look at the point at -3, 0. Since it bounces off the x-axis, you know that that point, that y value, the 0, is higher than or greater than any other point nearby. That's a local max. That's not an absolute max. Of course, it goes to positive infinity as x goes to infinity. And likewise, at x is about, I don't know, 3 point something, it's not quite 4, we have a relative min, where it's lowest to the least y value of anything nearby. Of course, that's not the real min. Absolute min, it goes to negative infinity, as we know. But okay, so can we figure out those maxes? Well, that was a little trick we had here here. We said, what if we find the max of this list? Okay, so I made a list of f of x values between -4 and -2 and stepping by 0.01. So it just makes a whole list of f of x's, like f of -4, f of -3.9, f of -3.8, well actually 3.99, 3.98, like that. So it's sampling a lot of values. And somewhere in there will be a max value, and max will list the maximum value in that list. We'll print out the maximum value in that list, and we got that the max was at, whoops, where? At -0.363 times 10 to the -26. Well, of course, it's round-off error here. If you round this off to the nearest 3 places in standard notation, not in scientific notation, what does -26 as an exponent of 10 mean? We're moving the decimal 26 places to the left, so there's 25 zeros in front of that 1. So it's -0.25 zeros, 136 something. So I would say that's pretty darn close to 0. So the maximum value is, let's say it's 0 to the nearest 3 places. Okay, so there you go. And how about the mins? Well, let's do the same thing. So let's generate a list. I don't want to actually print it out because it's a lot of numbers. So I'm listing from 3 to 4. Let me think about this. Okay. From 3 to 4, we're again sampling all the x values from 3 to 4 in 0.01. So 3.01, 3.02, 3.03. It doesn't actually do 4, of course. In a list, it always ignores the last one. So it goes all the way up to 3.99, I guess. And it plugs those all into f of x, and then we report the min. So let's find the min. Come on. And the min is -444.444. And there you go. So we can find maxes, we can find mins this way. Very nice. Where the mins and maxes actually occur is hard to calculate analytically until we talk about the notion of derivative, where the derivative is 0. We'll talk about that in the next unit, in fact. Because chapter 3 is our last pre-calculus unit. We're going to start talking about calculus. That's a unit. Calculus unit 1 is review of pre-calc. We won't do that. Calculus unit 2 is limits and the difference quotient. Calculus unit 3 is derivatives and calculus numerical derivatives and some applications. And calculus unit 5 is numerical integrals and some applications. And that's it. That's the last 3 units after we're done with pre-calc at the end of this quarter. Quarter 3 is ending up. Okay, so there's chapter 3, section 3, homework page 205, number 17, analyzing a polynomial function. And there you go. And that's our analysis. Okay, there goes limits at infinity, what the graph looks like, mins and maxes, intercepts, domain and range, all that fun stuff. And boom, done. I think we covered all bases as far as on Sage Cell. Okay, so have a nice day, guys. Don't forget your homework. Page 205, multiples of 5, where we did multiples of 10 the other night. We started talking about polynomials, power functions a little bit too. So, okay, so that's all there is to that. Bye-bye, YouTube. Hope that was helpful.